staring me down.
Oh, yeah. Yeah. God needs to take a chill pill. No, I got it after the class in English. Yeah. So it looks like no one cares about this game at all. Oh, I checked homecoming game. We don't have any tests Monday.
Okay, well, which question are we going to pose and us answer? Who we are and what are we doing here? Just in case, make sure that I'm not in the wrong class, you're not in the wrong class. So it looks like this is physical chemistry, which targets what? Prediction outcome of experiments, like NMR, UV spectroscopy, rates, activation energies of reactions. And this is kind of teasing factor. In fact, we are doing quantum chemistry, and more narrowly, we are doing some boring math. But this all should help us to answer posed goal and a sufficient level to give you trampoline for your career, whether it is science, research and development, industry, or teaching. What is the main outcome of today's meeting? What are we going to get? Any suggestions? Based on what we were discussing before, you can make an educated guess. And if you were browsing through any quantum texts or heard about I do not exclude that you will get the right word. So we are going to get one of the major principles that sit in the background of quantum theory, which will be principle
uncertainty.
Yes. So how do you formulate it?
Well, there's the space momentum uncertainty principle, which basically says that the better you know where the particle is, like the smaller area that you know it's in, the less you know about its momentum and vice versa. So like the more you know about one, the less you know about the other, just inherently, because there's no getting around it.
You can get out of here if you want to. Did you got what Vanden offered? Not quite, or you've heard something? Position and what? Momentum and what?
Position.
Yes, momentum and position are momentum and position are what?
Observables.
They are observable. Okay, they are connected. So these two observables have what?
Uncertainty.
Yes. So they both are uncertain. And the uncertainty of momentum and uncertainty of position are what? Connected. So the main message will be that you cannot have both position and momentum certain. In most of the textbooks, it is offered as a postulate or some paradigm without proof. Today we will harvest benefits from our math efforts. So we will get this uncertainty principle as an outcome of the writing long equations. So it will be not given to you as a statement, you will derive it easily. Of course, we cannot derive it generally for any system. We will derive it for for this crazy model of a lone electron in the empty universe. But then we can project it to other systems and think that probably it is universal. So we can basically that's it. And now we need just to have a math proof. And I do have a fear. I'm restricted from two sides. There is a chance to deliver this main message in 3 minutes, and what to do in the rest of the lecture. And there is another danger to go into lots of details, starting maybe from some comments about homework, and then being late for the edge of the meeting. But since you get the main meeting, you get main message. Probably you would allow me to invest a little of time about homework, unless everyone is happy and have completed it. Please give some secret signs if you're interested in homework comments. Oh, it's evidence signs, not even secret. Okay. So we are colleagues. We are on the one side of the trench against the science, against the theory. So me, you, and you between yourself. So I don't mind if you help each other with homework or consult. If you want to stand out of the rest of the class, I will give such an opportunity with a small research project which will be individual for everyone. But since we are on the learning curve on the very simple materials, do not be too competitive. Like, I do not give you a hint how I do it. I want to get better grade. No. If you ask and tell each other, it will be really beneficial for all of us. And I will give you a chance to stand out that no one can compete with you. Okay, so what about the in out. In and out. It's not corporation. Okay, it will be challenged for the next time. Zoom in and zoom. Can you zoom out with this remote?
You want to zoom in or zoom out?
Zoom in. Excellent. Thank you so much. Ah, it is our favorite picture. So first, how do you like Fourier transform from the Wikipedia or other sources? Or have you been confused, or you found connection between question number 0 and the rest of questions? Well, it's better to go over simple things rather than skip them. So, what is Fourier transform? Is conversion of a function of, let's say, x into set of coefficients. So we already do it in quantum theory. And this conversion into set of coefficients is by let's say from minus infinity to infinity in some limits, right? And escape sine with the same argument 2 pi x and somewhere dx. So we can. There is a way to convert a continuous function into set of discrete coefficients, encode, right? And then send a telegram to a friend like, here is the set of the coefficients, guess which function I processed. And based on the set of these coefficients, where n goes from like 1, 2, 3, and you can drop the series early enough if it is a good function and you are a good mathematician. So you send, instead of function which can be complicated, in Excel you like need whatever, few hundreds of points to have a continuous function. But if you expand it into these numbers, then you just communicate like handful of numbers, and you can reconstruct function back, and it will be very, very close to whatever we have, right? Of course, there are some limitations. This is for periodic functions, and there are they shouldn't. Well, if you would be mathematicians, we would set up set of boring restrictions like no division by zero in the function, no spike, something like. Good. I anticipated his answer on the number 0. It is what? 2 lines, summarized in 2 lines, right? Fourier transform. Of course you did so. Now, and you still bring homework. It is not the key. I leave you some room for creativity or to make mistakes. For example, I skipped the coefficient 0. It will be your minute of glory. And if you have these functions, a and b, then you can reconstruct your original function as summation. Is there a chance? Hello? Is there a chance to move this image to left bottom? Thank you. So you can represent your function as a summation of sines and cosines of different arguments. This expansion coefficients. So it is a useful trick. And now with computers being so quick and so powerful, we do not care much. But whatever, how many years ago, in 18th, 19th century, if we are French scientists living on different continents, and we want to send a postal dove with a function, you cannot roll too many numbers or make much drawing. But if you make up a couple of coefficients, it is condensed information that you can pass on. Okay? So, is it sufficient for doing number 1, or you want more coefficients? Give me a secret science. Do not hesitate. It will not. Thank you so much. It will not damage your chance for creativity. Is it clear enough? For some, yes. Anyone wants more coefficient or counts? No? But I want to give a count. So your function is periodic. If you go to L, 2L, 3L, you see it is the same. Therefore, we will use the same. Instead of integrating from minus to plus infinity, we will integrate from 0 to L. And some of you were talking to me in private, and I was lying. Well, not lying, not deceptive intentionally, just forgotten. Same idea as when you do expectation values. You need to normalize. So there should be a coefficient 1 over L in front. And then you can put anything in front and at the end, like A, 1, or whatever, equals. Then you plug in the function, and then you do first of the cosines. 2 pi, instead of n, you plug in 1, x divided by L. Almost done. One more count. The function is 1 up to L over 2, and is 0 after, right? Therefore, this integral can be split on two integrals, from 0 to L over 2, blah, 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 plus integral from L over 2 up to L, blah, 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 right? Which of the integrals will be 0? First or second? Second, yes, yes, because on the second interval the function is 0, so everything is multiplied by 0. So you take only over the half of the space. Okay, this should be sufficient to complete it. Is it clear about the question number 3, more or less? Yep. So it's very similar to what we did in class. You let me go? Not from the class, to the next slide, right? You don't want counts. Just identify full square, bring this into the shape of e minus y squared dy from minus infinity to infinity, which will be equal to square root of pi. And as a price of change of variables, identifying a full square, you will get some normalization, which will be exponential of some combination of the things. And they actually will be the answer, because this integral of Gaussian integral is trivial. So you bring it to trivial shape, and then see whatever comes as a factor on the front. 2x squared p sigma e to the power minus, not x, it will be k squared sigma squared divided by something like 4 or 2 or yeah. But sigma, which is very interesting, the sigma here goes not to the denominator but numerator. You will find it, like in the x space you have sigma in the denominator of this exponential. Here, if you do it carefully, it will pop up into the numerator of the exponential. Enough. I think you are well equipped to complete it. I did it this morning as an exercise, and it took about 40 minutes. So for one single run. Of course, if it is a failure, then I need to do it over. But, what else? You can also arrange a system of extra credits for bringing homework early. If you think like, if you do not need any comments, you can do it at evening when it is assigned, bring it in. If you're interested. Those are so little things just to help all of us to get through a bigger chunk of material. Okay, where did we stop last time? And what was our goal? This is probably right, but too boring, and you may have seen it in the recording. Okay, I have kind of summarized where we stopped on this little piece of paper. I will give a little reminder, introduction, what we are doing, what is our goal, so that it will be not a shock to dive into math right away. And the main message, the uncertainty relation, it is something really simple. We already debated it, discussed it verbally, and it will be maybe one slide with a simple picture. But to get to it and to feel ourselves independent derivers of equations, we need to suffer. So we have got a third way to do what with future? To predict, yes. And in order to go through this way, remember there was a simple quiz, not for you, for me, to see how you go through. That takes into 3 components: eigenfunctions, eigenenergies, and expansion coefficients. When we sum or integrate them together, we get the future. Remember? Something like this. Okay. And if we do it for our poor alone electron in the space, we take expansion coefficients from answer of last question of your homework. We have eigenfunctions as a plane wave, like oscillations in the space, and eigenvalues of energy will be same as in normal science before quantum. P square over 2m with understanding that P is h bar times k. This whatever index wave vector dimensionless momentum. Good. And then we did several manipulations because this integral that you were standing in front of, if you have a lot of wild imagination, one can identify a Gaussian function there. And one can identify Gaussian integral there. So integration goes from minus infinity to plus infinity. And argument, it is a polynomial of second power, which means one can identify the second power of some variable that is composed of everything that we have. Right? So the technical thing, how to get to this Gaussian integral, is three principles. Right now I'm not doing my job. It was something from math courses. So to identify full square, you need to find a square, b square, and 2a times b. And if you're towards going to your goal, you are missing something in your expression. You can multiply any term by factor, but as a price word, you divide by the same factor. Right? And also, if you're missing some term, you can add it, but as a price word, you immediately subtract. And when you do such manipulations, you can come up to very appetizing expressions that can be easily convoluted to something reasonable. So here is our full square that will be later placed as this integral. And this term that came up from adding and subtracting, and this factor that came from change of variables, but save time. You will do similar exercise in your homework. Come into here and there. So in fact, the integral gives trivial part, and then we need just to pull what are those terms. So from now on, or next minute, we'll stop being mathematicians and we'll become chemists again. So we will start scientific analysis what we have here. Okay. So B lowercase is this animal, and we need to plug in this A coefficient to the denominator and B coefficient colors to the denominator. Okay. What are we going to get? Well, let's maybe rush through, but I just give a little snapshots how we do it. So the factor in front, of course, it is important if you do it for the grade, but not in the class. For our major answer for our scientific analysis, right now we can temporarily skip it and focus only on this factor. Now, B is minus ix, and we need it squared. So x squared clear, I squared minus 1. So it will be e to the power of minus x squared. And in the denominator, upon taking the square, we have 4 times a minus sigma 0 over 4 minus I h bar 2 masses times time, close the bracket. What do you get? It's our future that we have predicted. X, comma, t. One more beautiful colors. And we multiply it by some constant, which we don't care right now. So we are ready to do science. What can you tell about redraw it so that it doesn't interfere with this little exponential? And this whole thing is in the power of exponential. So let's analyze, let's think about this function. What does it tell to us? First, interesting. See, this 4 can cancel with this sigma, which is good. So how does it compare with our initial condition? So there is a simple sanity test to self-correct. And I need to be first in doing it all the time because I'm doing it all the time. It's so easy to forget plus, minus, a factor. So one needs to have some way to check it. So when we were scientists last time, we did agree that our main question is to see whether electron will expand or shrink. And in order to test this hypothesis, we set up initial condition as psi 0 equals e to the minus x square here, divided by sigma 0, right? Gaussian function. Good? Then I have invited you to believe me, which formally you do not need to. You may just check and require me to prove each step. But this was wave function at time equals 0, t equals 0. And now I want you to believe that we have the future, wave function at any time in the future. But if our solution is correct, then if you plug in time equals 0, we should get back the initial condition. Well, if time equals 0, then in the denominator we have only this sigma sub 0, right? I think there should be pluses. Yes, now everything is clear. Good. So by plugging in time equals 0, we reconstruct back initial condition, which means that there is always chance to be wrong, but probably not this time. Are you happy with this function? Do you look at it and become happy? Some of you do. Partially. I'm not yet happy. What makes me unhappy just as a user? If I hire a mathematician and he brings me this function. What did you brought me? How do I plot this imaginary unit? I want probability distribution and you give me some function. So this imaginary unit it could be correct, but it is not convenient for intuitive analysis to think in the complex plane or whatever. And you are certified experts in postulates of quantum mechanics. You taught me something about probability, wave function squared, right? So the meaning is not, the physical meaning is not behind wave function. It is only in the wave function squared and expectation values. and eigenvalues. So in order to become happy, I invite you to take this wave function and do a little trick with it. Make it psi star times psi and see what happens. You can try doing it in your notebooks, and I will see if I have appropriate slide. Start of lecture level. Okay, it was introduction. Okay, so this is what we are going to get. And it's not a big secret, we just will prove it. So after taking the probability, the psi star times psi, we are going to get the Gaussian function again, but without any crazy imaginary numbers. And we would be able to bring it into the shape with initial times a coefficient which shows expansion in time. So the original hypothesis that electron is so aggressive that it wants to take all available space is probably correct based on this calculation. So it will become fatter and fatter instead. And let's get to this point with a little more details. So it's expanding. I'm celebrating laziness today. I'm just showing the questions, but it's very bad. It's bad both for me and for you. It's much better if I read it before.
Can you go back a slide quickly?
Yes.
There's a question. Sorry, back one more. All right, I have no idea where we were. I guess I'm confused on what is the n squared.
Normalization.
Oh, it's the normalization.
Yes, yes.
Okay.
Wave functions need to be normalized, so that integral of wave function square will always be equal 1.
Okay.
And we can always find it, but if you are short in time, we can leave it for the future.
Okay.
Or if you have some reasons to skip it temporarily, just for the sake of time. Okay. So here is the wave function psi, and here's the wave function star. How do they differ?
The left is the complex conjugate.
Hmm?
The left is the conjugate.
Yes, yes. So how do you, if you have a function, or just well, it is already written here, but I write it once again. So e to the power minus x squared divided by sigma divided by something. T divided by m. So what does it mean, complex conjugate? What does it mean, this star symbol? I know that.
Anytime you see an I, you just change the sign.
Right? Did you hear it? I don't know what you're doing in class. So wherever you observe symbol I not like a person, I like a letter, mathematical symbol. You swap the sign. If it was plus, you make it minus. If it was minus, you make it plus. And then it is your wave function star, complex conjugate, right? So it is what we have here. It is plus at this place and minus at this place. How do we multiply these two exponentials? We add together their powers, right? And we want to be good cooks. We do not want to eat raw food. We want to cook it so that it will be easy digestible. In math, it means like factorize it in the shortest possible form, like try to simplify it. You can be correct, but hard to digest. So, and here, how do you do it? If you have summation of two fractions, denominator, which denominator?
One.
Common what?
Denominator.
Okay, so if we consider this little thing x as a, x squared, and here is another x squared as like a, and this denominators with minus, we can call it b, and denominator with plus, we can call it c, and then you multiply the denominators in the new denominator and you sum them in the new nominator, right? No one objects. And if we do it carefully, I promise I use it in the past. And you can practice it if you like. But what happens? What happens? So if you take this b and c, you multiply it in the denominator and sum them in the numerator. When you sum, then this part with imaginary unit comes once with plus and other times with minus. So they cancel, which makes easy numerator. And in the denominator, what do we see? Another little trick from middle school. X plus y times x minus y equals what?
X squared plus y squared.
X squared. And which side goes to? Huh? Minus. Minus y squared. Right? This doesn't surprise you. So we replace this product of x and y onto x plus y, x minus y, onto x squared plus minus y squared. And we get the plus sign because our y contains imaginary unit. Okay? So let's, is it visible? Is it large enough to see? No. Okay, then I need to expand it. Please. So it was x squared times sigma squared over 4 plus da. And what I just wanted to point you on, that sigma, 1 power of sigma cancels. And then after this manipulation, is this visible? Then we are getting again Gaussian function as decreases as x goes to plus or negative large number. And here we do have the width plus some expansion coefficient and t squared. And this t squared came from algebraic manipulations. We didn't guess it. We obtained it as the result of this processing. So we set up a goal, did some, applied our protocol of predicting the future, performed mathematical manipulations, and got this answer. This is something that we can analyze as scientists. I was not lying, or I was lying acceptable meaning. So this is a Gaussian wave function that has this shape as function of x. And at time 0 it has 1 width, and as time passes by, you get it broader and broader, right? So whatever stays in the denominator is the width of the function. And this width, we can write it n square e to the power minus x squared divided by sigma x of t. And the sigma x of t is how broad, how far this electron did expand in the space. So if we draw this sigma x as function of time, it starts from initial value, and what does it do later? Does it decrease or increase?
Increases quadratically.
Increase quadratically. So this is base value. So appetite of this aggressive expansion becomes more and more. So it takes more and more space. Good? No objections. Now, let's have a second glance. On the answer of your homework, which is right here. So, you're not going to derive anything, or almost nothing. But prepare. Right now, there will be an important message worth of translating into your own words and writing down or memorizing. So there I'm very clear in mind and just try to find best words. We got acquainted with two types of space. We got regular position space, x, and we got momentum space, p, or we can call it k. And your homework assignment was to get expansion coefficients for predicting future, but on the other hand, it was recasting your wave function in the momentum space. So we converted from the space of position in true space into range in the momentum space. We saw that wave function with this momentum we have larger expansion coefficient, with another momentum lower expansion coefficients, and then we have distribution of this plane waves with different values of momentum. This representation, this expansion coefficients, is a replacement of wave function in a position space, and it is the same object, the same function, but it can be represented in different spaces, in our regular, intuitive, simple position space, and at the same time at the momentum space. So the answer from your homework is wave function in momentum space. Wave function in momentum space. This was statement number one. Now, if you know for sure that our electron has only one value of momentum, that it is like a plane wave moving with given velocity on one side, then momentum is certain. Right? Or if you know for sure that our electron is classical path approximation is pointed at a very, very narrow vicinity, then we can call that the position is certain. But if it has width, then it means it is uncertain. The amount, the width, the value of this variable sigma is uncertainty, is plus minus how much it deviates from central point. I don't know how to say width. H equals uncertainty. Width is uncertainty. It was statement number 2. Now, statement number 3. Let's look on our answers and analyze what is uncertainty in position, what is uncertainty in momentum. In position we discussed it, in momentum we can recast this equation that you get in your homework in this form, where you get p squared over sigma sub p. Where this sigma sub p will be to a sigma x. We just redefine it. But what is really interesting, the distribution in momentum doesn't change in time, at least for this problem. So the width uncertainty of momentum remains constant. Uncertainty of position changes, uncertainty of momentum doesn't change. If you need to go to other class, please go forward. It is recorded and you'll see it. Now, a little math. It is exactly 11:50 right now. Now, let's try to multiply these two things: uncertainty of position and uncertainty of momentum, which we already know in exact answers in radical. So here is our uncertainty of position that grows and uncertainty of momentum that doesn't grow. So we just take these two functions and multiply. So if we do it very carefully, we see that many things can be cancelled. And what is important is here we have sigma 0 in numerator, here in denominator, and they cancel. Cancel here, cancel 0. There. So, and at time 0, second term doesn't apply, right? So it will grow later, but initially we can tell that it is 0. What do we get? H bar square with some factor. H bar square. Here I'm getting divided by 2, but the factor doesn't mean is not so important. It is important that product of uncertainty of position and momentum uncertainty of position and momentum are not independent. They are connected in the following way. Their product gives specific mathematical relation. So it is equals h bar square plus some coefficient alpha times t squared. Right? Which means that sigma x times sigma p, so it can be equal to h bar square over 2 at time 0, but later on it will be always bigger. Right? So it never gets smaller. It can stay the same or expand. So our original hypothesis that electron is so aggressive that it wants to play civilization and expand on new continents, this property of electron to take more space, results in philosophically important principle of quantum theory, which is known as uncertainty principle. So because it we found that it wants to expand just because of our ways to predict future, but later on, logically, because we found its tendency to expansion, we recast it in the form that position and momentum cannot be measured simultaneously with arbitrary precision. Or, in more mathematically, the product of uncertainty of position and momentum has some minimum value, and then it always grows. Right? So, sigma x sigma p grows with time. So it has some minimum. This h bar square thing is a minimal value of uncertainty. position and momentum can be known precisely. They have uncertainty. Okay? I hope that when I click the button, it will be my favorite slide. Yes. Okay, thanks much for staying. I have good intentions to return those minutes that I borrow and accumulate from lecture to lecture. Meaning that one time you will either cancel the lecture or go away like half an hour earlier. So I'm trying to count and accumulate. Thanks for staying. And see you on Wednesday. See you and your homeworks.